Yeah, so any doubt from last lecture where we covered the SIR model? Is it clear to everyone about how whatever we discussed in SIR model, how you can numerically use various methods? Like you can, in fact, what you can do is just use Euler's method to do the, the trajectories or the behavior of all these different variables under different conditions. That means you should take set of different values of small r and a and see what comes out under what circumstances you put in some numbers for different initial conditions, what kind of situations you get. So that's anyways, probably I'll give you an assignment.
Excuse me, sir.
Yes.
So before we begin, sir, I just wanted to ask.
Can you be a bit louder? Some of your voice is very faint.
Sir, can you hear me now?
Who is this?
Sir, my name is Krishnanda Marathe.
Yes.
So it's just a little doubt that the value q equals to r by a. So can you just explain the significance of it? Like, what does it represent in it?
No, I had mentioned. So basically, if you look at Q, see Q comes in front of this. I mean, even when we wrote down the equation of I, how the number of infected people are changing. See, that is related with this. So this is what it is, right? Now, if you look at the first term, R basically tells you that how susceptible a person from the susceptible population, when they come in contact with an infected person, how likely or what is the probability with which they will become infected. So R small r captures that fact that, so like I said, that I gave an example that suppose if you are coming face to face with an infected person without a mask, then effectively your value of small r would be very high. In contrast, if for instance, both the infected person and the susceptible person, they wear a mask, then the probability that the susceptible person will become infected, that would relatively be less, and correspondingly the small r value would be less. That is point number one. Second is that if you look at A basically tells you what is the recovery rate, right? So A basically tells you even if a person is infected, how fast do they recover? So in some sense, if you look at this ratio R by A, it is a measure of what fraction of the population are likely to get infected. So that's sort of the physical understanding that so if the likelihood of lot of people getting infected from a susceptible population, then the Q value would be high. So that is the sort of physical meaning of high values of Q. And correspondingly low values of Q, see, low values of Q, it can happen in two ways. See, one is just imagine a situation, even if this R value is high, that means people are very susceptible to get infected. But imagine hypothetically that although people are getting infected in a very small, with a very fast rate, they recover. Even in that case, your Q value can be low. Typically, what is seen is that what you can control during an epidemic is not, you do not have so much control over the value of small a. Small a would be typical for some particular disease. Like for instance, for corona, the typical recovery time is 14 days. So you can calculate whatever is the rate of recovery, whatever, 10 to 14 days. Whereas Q, small q is small r is something you can change by wearing mask or having social distancing, things like that. So that is more from practical point of view. But overall, that means overall this ratio is what tells you. I mean, if you think of it, Q is actually a dimensionless number, right? R is rate, so this is units of 1 by time. A is also 1 by time. Q itself is dimensionless, but it basically measures that how likely the disease, I mean, how likely, first of all, the disease is going to spread or to transmit from a susceptible people to an, meaning how a susceptible people become an infected. So that's the interpretation. Okay, I think we will start now. One second. So today the topic that I'm going to cover, rather, it is a continuation of methods of solving differential equation. And what we are going to discuss today is solving second order linear ordinary differential equation for boundary value problems. For what kind of boundary? I mean, the crucial point is we had already the different methods. In fact, during the initial lectures, I had discussed about how one solves a second order differential equation for the initial value problem. That is something we had already discussed, right? That solving second order ODE for initial value problems So what was, one second. So what was the prescription? I mean, I'll just very quickly because we have done it. So you have a second order differential equation and you define a new variable, let's say Z, which is just the first derivative. And what you realize is that you can effectively write a second order differential equation into two first order differential equation. And if you have the initial value problem, for initial value problem, recall that means your value of the function is given at whatever. I mean, it can be at any point, let's say x equal to a, and let's say we call it ya. And you have the derivative, which you would call z, let's say, and that is also given at x equal to a. And let's call it y prime of a. Given this initial conditions, then you can use either the Euler method or RK2 or RK4 that you learned to solve the problem. So you have the initial value of the function and its derivative, and then you find out what the solution is. So this is something you already know. Now let us, for second order differential equation, like you know that it can either be an initial value problem or a boundary value problem, which you have, whether I mean you have encountered, of course, in different contexts, like in quantum mechanics, whenever you deal with time-independent Schrodinger's equation, whether it's potential in a box or harmonic potential, there it's a boundary value problem. So what is specified is that you know the value of the wave function, for instance, at the two boundaries is known, depending on again the context. And then you have to find out what is the wave function by solving the Schrodinger's, the time-independent Schrodinger's equation. That is one example. Another obvious examples is in fact Newton's equation solution. That is again a second order differential equation. So you can, for instance, let's say, I mean, one of the problems that we have seen for a long while is this problem of, you throw a ball trajectory. And let's say that means, suppose you do not know the initial velocity, you know the initial position and the final position. So many such second order differential equation, you either specify the initial conditions or you can specify the boundary conditions. And so what is the boundary value problem? That means what you know is you are specifying that y at some, let's say x equal to a, so let me just write it as yk, it is given by some value. And similarly, the y at b is another some boundary value alpha and beta. And you have some underlying differential equation that you want like to solve. Question is, so let me write a second order differential equation, the general form. So the general form would be where, of course, I have used the notation y prime is nothing but first derivative, the first full derivative, and y double prime is the second. This is a general form for, of course, ordinary differential equation, but notice it's also a linear because the method that I'm going to discuss is for holds good or works very well for linear ordinary differential equation. What do you mean by linear? That means if you notice, there are only terms which are linear in y. So instead of this form, if I had y square, or in fact, if there was a functional dependence on y in v or u of x, then in that case, or if you have second derivatives or third derivatives of y prime, that case, of course, it would be a nonlinear equation. So the method that we are going to discuss for solving numerically a boundary value problem, and this method is also called Shooting method, is valid, works very well for this class of linear ordinary differential equation. One can also try using it for nonlinear, but in that case, there can be serious issues, may not work. So first thing is, given, let's look at this form of this differential equation. What is the problem with this? What is the problem in solving it numerically? Now go back to what you did for the initial value problem. Let's say, Euler or RK2, but let's say what you did in Euler method. You have to couple differential. First step that you did was you took this second order differential equation. You defined a new variable z, which is first derivative of y with respect to x, and then you landed up with these two first order differential equation, one involving derivative of y, one involved derivative of z. And then how you evolved was that Euler's recursion relation, it basically allowed you to calculate the value of z at I plus 1th iteration and relate it with the value of z, which is nothing but the derivative, at the previous iteration step, and similarly for y. So since you knew the value, since in the initial value problem, you knew the value of the function y at x equal to a, and you knew the value of the derivative, that means z, which was derivative of y with respect to x at x equal to a. And with those initial values, you just use those recursion relations of Euler and were able to find out the solution of second order differential equation of this. So far, so. Now that you have a boundary value problem, that means you know the value of the function at x equal to a, and you know the value of the function at, let's say, this is your x equal to a, and this is your x equal to b. You know the value of the function, whatever it is. This corresponds to y at a. And let's say at x equal to b, question is that if you had gone back to your Euler method and you wanted to solve it using how you did it for the initial value problem, the problem that you'll encounter is that you do not know the initial slope, right? The actual solution of this differential, let's say this is my, what I do is, let's say this is my actual solution of my differential equation, which I plot. Something, let's say this is this. This is the actual solution. Now, here because you do not know what is the initial, seeing the initial value problem, you know what slope to begin. You knew the value of the function and you knew what was the value of the slope at x equal to a. And that's why you could just evolve it and you could reach till the point where x equal to b and get the entire solution. Here, let's say, so you have to take a guess, right? You might say that, okay, I will begin, I use this Euler method, but I will take a guess value of the slope. I would say that, oh, I will take some slope, which is some value. So let's say I begin with a slope of 0. So your initial slope, let's say you start with slope 0. Now, if you start with this, see, the actual differential equation has actually a different slope, but you are guessing, which in general will not be the true slope with which this differential equation is supposed to evolve. So now that you begin with a slope which is different from the real thing, you can still evolve it. Now you can use the prescription of Euler method, like this two coupled equation, either Euler method or RT2, and you evolve it until you reach this point x equal to b. But because you have started with a different value of the slope than the actual solution, you will probably land up with somewhere, let's say, I'm just giving an example. You will not land up in the correct position. That means, in fact, the value of the y that you will get with this particular slope which you are forcing this differential equation to take, when you reach x equal to b, you would reach at some other point, right? Does all of you agree? Is it clear to everyone or not? Because it's a crucial point. What is the problem? That because you do not know the value of the slope, so you will land up in a different position. So now what you do is the following. So how you use this method is that you actually take you say that, let me call this differential equation 1, and these boundary conditions, let me name it 1a and 1b. Consider a solution. Consider a function of x, a function which I call y bar of x, such that y bar satisfies 1. I consider a function so that y bar satisfies 1, and I would call this function y bar at x equal to a takes the value which is same as what you see here, same as the left boundary condition, and this y bar is defined by taking the derivative at x equal to a, and that, so in principle you will have freedom. I mean, this method doesn't depend on what particular specific value of derivative you choose, but for convenience, let us say it starts with the derivative 0. So when I say that this differential, this y bar, this function which you are defining, some new function, which satisfies this differential equation, I simply mean, that means if I had written down the differential equation for y bar, this would have satisfied this form u plus, I mean, I'm just suppressing the labels of v and x, but basically it would satisfy this. Clear? So it satisfies this differential equation and it satisfies these two boundary conditions. That y bar of a is equal to alpha, and the first derivative of this function y bar is evaluated at x equal to a is equal to 0. And of course, this function, like I told you, would start from this value of x equal to a, and when you reach x equal to b, it will reach some point. So this is my first function. So let's say, let me call it equation 2. Consider another function which I call y tilde of x, such that y tilde again satisfies this differential equation So it satisfies this differential equation with conditions, with boundary value conditions where y tilde, if you evaluate it at x equal to a, that this again gives you alpha, and y tilde prime, that means the first derivative of y tilde with respect to x evaluated at x equal to a. Let's say this takes a value of 1. And again, I am stressing, so this let me call it equation 3. Again, I am stressing what you have in this, within this method, you have the liberty to choose what value of y bar prime evaluated at a. Instead of 0, you could have taken some other number. You could have taken half. And similarly, this y tilde prime, which I have taken to be 1, you could have taken some other value, let's say 1/4 or 5. So basically, here I'm just for often it is convenient in the sense that here I have chosen a special condition that in one case, basically, that means in one case the slope, the initial slope of the function I have taken to be 0, and in the other case the slope is 1. The only care that you have to take into account is they should not be same. They should be different values. So that is one thing that you should keep in mind as far as doing the numerics is concerned. So now that you have this, what I'm going to claim is that, of course, these satisfy the following thing. We are going to construct a function y. So construct y, which is a linear combination of these two functions, y tilde and y bar. Y tilde and y bar would be some, function which would evolve according to this differential equation. And in general, of course, at x equal to b, they will not coincide. They will, in fact, they will not coincide with this original function. They will land up in two different places. But we construct a new function, let's say y of x, which is a linear combination of these functions. That means y bar of x and y tilde. Let me call it equation 4. So is it clear up to here? Now, what is our task? So I'll just trace out the route before I actually do it. I want to, so at this point, we still do not know what is lambda. Okay. What we want to do is that we actually finally have to find out lambda for the purpose of finding out the solution. But what we are going to actually demand is that this linear combination of y that you have arrived with using y bar and y tilde, that this is going to satisfy my original differential equation. That is something I have to check for. First, I have to check for what values of lambda it is going to satisfy this original differential equation. That means for what values of lambda does it satisfy, first of all, this original differential equation 1? That's the first point. Second is, we would demand that this linear combination also satisfies the first boundary condition. That means this. That's the second thing. Third thing is, we are going to demand that that differential equation or solution that we have is also going to satisfy this last boundary condition which we actually are interested in solving. See, problem with y tilde and y bar is that they are not the correct solutions because they do not satisfy the correct boundary condition at x equal to b. And we are interested in finding out that correct solutions, and how we are going about doing it is by constructing first a linear thing. And like I told you, these are the steps that I would like to check. So let us do that. So in fact, focus your attention on equation 1 and 2. You can convince yourself. So if I
Sir,
Yes.
sir, I'm
Please go
sorry to
ahead.
interrupt.
Yeah.
We have another 1b condition, yb equal to beta. So are we using that anywhere?
We would use it. That's what we would come to.
All right. Thank you, sir.
That's what I'm saying. That we are, I'm just leading out the steps, but I'll show it. Eventually, we would want this y to satisfy three things. So this y that we are constructing using this y bar and y tilde, this has to satisfy three things. First of all, it has to satisfy the original form of this differential equation, which is given by number one. Second, it has to satisfy the two boundary conditions that I want to solve, namely 1a and 1b. That means the y that I am constructing out of this linear combination has to satisfy that first boundary condition. That means it has to satisfy 1a, and I would also demand that it has to satisfy 1b. Right? Only when they do it to be arrive at our solution. So that's the A. So now what I'm saying is that first of all, let us check one by one. Does this linear or under what conditions this linear combination of these things satisfies the form of the differential equation given by this? So now that you have that, so you basically, the prescription is, in order to check, you focus on 2 and 3 and 4. So multiply equation 2 by lambda and multiply equation 3 by 1 minus lambda and add. So you do the addition. In order to save time, you can convince yourself. So that means I multiply it by lambda. This equation I multiply by 1 minus lambda. So just to illustrate, and rest you can do it as an exercise. So what would be the left-hand side of these two equations when you do the addition? It would just be lambda. So this I'm writing the left-hand side. Left-hand side would be lambda y bar double prime plus 1 minus lambda y tilde double prime, right? And what is y tilde? See, these are linear equations. That means if I write down explicitly, this is nothing but del square y bar del x square plus 1 minus lambda del square y tilde del x square. Okay. And because it's a linear operator, I could have taken this out and written it in this fashion. Like it here itself. So the next step is, so the left hand side is basically, you can take the derivatives outside, the two derivatives, and what you are left inside is lambda times y bar plus 1 minus lambda times y tilde, and this whole quantity is nothing but whatever is the y of x. So the left hand side just turns out to be y, which is in shorthand, which is just y double prime. I want you, since you have done this, the rest I'm not explicitly showing. This I leave it as an exercise. You can convince yourself that, like I said, you follow the steps. Just go through the steps. You can convince yourself that when I substitute, indeed for any value of lambda, in fact the lambdas will cancel out, you will see that y bar, y double bar would be equal to u plus vy plus wy prime. In fact, all the lambdas will cancel out. You do it on the right hand side and you will get the answer. This is the first thing. So irrespective of what values of lambda you choose, this linear combination of the solutions of y would satisfy the equation 1, the form of the differential equation, which we had demanded at the beginning. What about when we impose the condition that, what we are demanding is, if you see this relation, you are demanding, let us find out what is y of a. again, for finding out y of a, you have to go back to equation 4 and substitute. So y of a is equal to lambda times y bar evaluated at a plus 1 minus lambda times y tilde evaluated at x equal to. But we have already, y bar of a is equal to alpha, and similarly, y tilde of a is also equal to alpha. That was the condition we had chosen. So you can just replace it with the value. That means lambda alpha plus 1 minus lambda times alpha. And if you do the thing, what you find is y of a is again what you find. So for the first two conditions, what you find is that indeed your y of y evaluated at a gives you a value of alpha as you would like, irrespective of what values of lambda that you choose. So we are through with the first two conditions. Now we would like to impose the last condition. And what was the last condition? The last condition that you would like to impose is the following. Y at b. Remember, what are we demanding? That this function that you constructed by linear combination of this y bar and y tilde, that linear combination has to be equal to beta. Has to be equal to beta, right? And we go back to step 4. And what? So that means y evaluated at b is what? Maybe I can use this since that. So y evaluated at b is basically lambda y bar at b plus 1 minus lambda y tilde evaluated at x equal to b. And I'm demanding that this has to be equal to beta. Fine. This is what I'm demanding, because once I demand this, then only I'll be able to construct my entire solution of the differential equation with the two correct boundary conditions, right? Because my y at x equal to b has to be equal to beta, which is given by it. Now you see that if you look at this equation, then what does it tell you? So you can separate out the variables. So now you see that unlike the other two conditions, this condition does not hold for all values of lambda. In fact, it fixes the value of lambda, the constant which you had started off with, which you did not know. In fact, your task is really to find out that constant, that only for a specific value of that constant, this would be satisfied. And what is that value of constant? It is rather easy to see. You can easily separate out, y bar b minus y tilde b. And this, if you take on the other side, this would be beta minus y tilde at b. And therefore, the value of lambda that you get is beta minus y tilde evaluated at b divided by y bar evaluated at b minus y tilde evaluated at b. Okay. Notice, this is crucial. Beta is something which is already known because it is given to you. You have to solve a differential equation for certain boundary conditions. So beta is known. That means the value of y is known. So you know beta. Y tilde evaluated at b is something again you know. How do you know? Because now that you know the Euler's method, you have decoupled those differential equations, starting with that initial y tilde, remember, corresponding to initial slope of 1 for our case. So you know in principle what is y tilde, the value of the y tilde at x equal to b. Similarly, you know numerically if you solve the differential equation using Euler method or RK2, then you know y bar value at x equal to b. You know again this. So basically on the right hand side you know all of this, and that's why you know lambda. And now that you know lambda, Since you know lambda, now look at this. You know the entire solution because your y of x, you know that what is that value of lambda. You of course know the functional, since you have solved the Euler equation, you know the entire form of y bar of x. Similarly, you also know y tilde of x, and since you know this, you know lambda, you are in a position to find out and construct the entire solution for the differential equation, which corresponded to equation 1 with those boundary condition which was specified by a value of y at x equal to a, which was alpha, and y at x equal to b, which was beta. So in principle, that means you have managed to numerically solve the differential equation. So let me again just summarize the numerical steps that would be required for you to solve this problem. So first step is, in any case, you have to take two guess values of the the two different functions. The value of the slope at x equal to a, you have to take two different guess values. For each guess value, and with the boundary condition that y at x equal to a is alpha, you have to use the differential equation, decouple those second order differential equation into two first coupled equation as we had discussed in earlier class. You have to do it for both this equation. And from there, you would be able to construct the entire solution, which is y bar of x and y tilde of x. Once you have obtained y bar of x and y tilde of x, you know what would be the value of y bar of x and y tilde of x at x equal to b. Since from there, once you know the value, you would be able to find out what is the value of lambda. Once you know the lambda, then you would be able to construct the entire solution using equation 4 numerically. And that solves the problem numerically of finding out the differential equation solution using this. And just to add, I told it for Euler's method, but you can do it even for using the RK2 or RK4. The intermediate steps, you can use any of this. So this is sort of summary of the shooting method. I should also like to stress that if instead of a linear equation, if it were a nonlinear equation, this method doesn't work, or in the sense it is not going to be exact. You can check why it doesn't work. So I will stop here for today. And whatever, if you have doubts, I'll take questions. And tomorrow, what I plan to do is that tomorrow I will not write anything. I would rather be available for any until now whatever we have covered, or whatever difficulty you had in writing the code, or something you did not understand regarding the assignment, or whatever. I'll also give assignments related to this. So all this thing you can have a look, see if there are some points which are not clear. And those doubts I would clarify tomorrow. So tomorrow I'm not going to write anything on the board. Rather, I'm going to address in this specified time, tomorrow at 10:20 to 10:50. I will address the doubts, for all the doubts until whatever we have covered until now. Yeah. So I will stop here. But if you have any questions, I'll stop the recording. But I can answer your questions. So that's yeah.